Thank you, Professor Xie, for the kind introduction and also the very generous invitation. Truly an honor for me to attend this science symposium today. And you probably could feel the pressure on my shoulder right now, speaking after the titan in our research field. Professor Zhou is always the role model that our younger generations always look up to. I'm truly excited to be part of this Science Prize Week. Personally experienced the joy and the passion when we celebrating the achievements of great science. I was trained as a synthetic chemist, and nothing more have made me more prouder than that. So, chemical synthesis have contributed to all the molecules, materials that help us to advance human society. Over 90% of all chemical processes rely on catalysis. So from the fuels in our cars and to the medicines we take. And there are statistics to show that about 1/3 of the GDP is contributed from catalytic process. So catalysis is truly the invisible engine of our modern society. So this is a typical scenario where catalysis is taking action. So on the right side, showing a classic transition metal catalyzed processes where we make acetic acid. To the general public, if you have trouble recognizing these chemical name or the structure with this formula, you probably have tasted a lot of this. It's the main component of vinegar. It goes easily or goes perfectly with seafood. So in industry, we are making this basically from two toxic materials, methanol and carbon monoxide. You probably don't want to taste either of those. But simply mixing those two abundant or inexpensive materials, no chemical transformations will happen simultaneously. This is where we have to overcome a significant amount of activation energy, where chemists tend to call high activation barrier. So we have to develop elegant catalytic processes where we try to insert or activate this CO bond to generate methyl iodide as the intermediate, where then rhodium metal comes in to insert into that, then to couple with carbon monoxide to form the CC bond. So as a matter of fact, most chemical processes rely on noble metal catalysts, such as palladium, rhodium, or iridium. And to overcome that significant activation barrier, we have to enforce like high temperature or high pressure conditions. And most of the time, it tends to generate large quantities of acetic waste. So it will cause a lot of ecological burdens on us. Of course, synthetic chemists have realized this challenge in sustainable synthesis. How to cut down cost, how to reduce waste and energy consumption. So nature, on the other side, are constantly making chemicals in their factory, in living cells. So in the keynote speech, Professor Washer has shown lots of exciting examples in enzyme catalysis. What I show here is the ultimate model of green and sustainable synthesis in this photosynthesis system, where you can leverage carbon dioxide and oxygen and water as the building blocks to make sugar. So, of course, nature involved so many years and come up with a rather complicated system that allows it to leverage photoexcited electron transfer and charge separation processes. So basically conduct chemical transformation, especially electron transfer at excited states, then bring down the activation barrier, allows the operation to take place under ambient conditions. So us synthetic chemists, of course, can take an important lesson from this. But we are certainly not the first one to look at this perspective. Almost 120 years later, earlier, a pioneer in Italy have already started to take action. So they found out that if we were to put a solution of this indole compound on the left side in a glass flask and put it on the balcony, and after a whole summer, it can be converted in a rather complicated polycyclic product. So Chen was really a pioneer to initiate the photochemistry. And they are true visionaries, because I think probably over 100 years ago, working down this balcony, look at their amazing results, they probably have to think in chemical processes would look very different in the future. To quote them word by word in the article published in 1912, they are thinking there will spring up industrial colonies without smoke and without smokestacks. So forests of glass tubes will extend over the plains. Instead of this will take place photochemical processes that have been the guarded secret of plants. For life and civilization will continue as long as the sun shines. These are truly beautiful words. And even AI can, based on these words, to create a picture. But of course, 100 years later, this goal has not been achieved, not yet. To understand why, we probably need to go behind the reason of this chemistry, this exact excitation mode. Because you see, the physical chemicals we use, night alkenes or alcohols or ketones, they only have very simple functional groups, CH bonds, CC bonds, or double bonds. And those type of bonds tend to only absorb high energy UV light due to the large HOMO-LOMO energy gap. After excitation, they tend to form like triplet state, which are rather reactive and cause a lot of like reactive pathways. For synthetic chemistry, it's truly challenging to control them. And if you try to excite the CH bond and make a photochemical transformation, chances are you are going to excite the CC double bond or CO double bond in the solution. So basically, this non-selective excitation pattern will cause a lot of challenging in selectivities. So almost like 50 years later, when synthetic chemistry started to merge photons with transition metal photocatalysts, we start to see a viable solution. They start to take this photochemistry to a different level, open a new area of limitless potential. So synthetic chemistry started using like polypyridine ruthenium or iridium complex as photocatalysts, because those photocatalysts can absorb visible light energy through a metal to ligand charge transfer excitation processes. Those processes tend to generate a long-lived, a rather stable triplet state, then itself can undergo single electron oxidation reduction or energy transfer activation patterns, allow us to build elegant catalytic cycles to achieve selective activation of our organic molecules based on redox potential or triplet energies. But not so many metal complexes can absorb visible light and have a relatively long excited state. So this is where we started thinking. And we noticed there's a different type of excitation mode has been previously reported in the literature. The electrons will flow the reversible way. When excited, the electron from the filled ligand orbital will be promoted to the empty orbital of the metal center. It's called ligand to metal charge transfer excitation. One peculiar feature of this excitation mode is that it tends to promote the coordination bond homolysis, leading to the generation of a reduced metal center associated with oxidized ligand center radical. Basically, your photoactive species have been turned into two different parts. And for people who are familiar with catalysis, this is truly not a good thing to develop a photocatalyst. Because the lesson we learned in the past is that we have to have a long-lived triplet state or long-lived excited state allow us to interact with organic molecules. So we actually found a simple solution to turning this decomposition into catalysis. We took a simple lesson from transition metal catalysis, where that most of the time, the active species are generated in situ through in situ coordination, either ligand and metal or substrates between the metal. So if we were to merge LMCT excitation with in situ coordination, LMCT excitation, and homolysis, we could convert the transiently coordinated hydroatom functionality into the open shell radical intermediates. That would help us to address the selectivity challenging in the generation of radical intermediates. And since LMCT excitation has been commonly reported for a variety of high-valent transition metals, especially those earth-bound metals such as cerium-4, titanium-4, iron-3, and copper-2, that gave us a very good chance to develop more sustainable photocatalysts. So over the last 3 years, we also realized that LMCT catalysis not only gave us a straightforward activation mode to generate radicals, it also gave us a versatile catalytic platform to us to merge 1 electron open shell activation modes with 2 electron transition metal mediated processes in a single catalytic framework using 1 metal catalyst. So based on this design blueprint, our research group over the last 10 years have mainly focused on 2 things: the selective activation of sp3 CH bonds in feedstock alkenes, and the selective cleavage and functionalization of sp3, sp3cc bonds in feedstock chemicals, both of which are recognized as grand challenges in transition metal catalysis. So we managed to leverage hydrogen atom transfer elementary steps and the radical mediated bond decision steps, then to achieve selective transformations of these inert bonds, which previously have been recognized as the molecular framework. We're especially interested in developing new catalysts or new catalytic transformations. We also try to demonstrate scale-up applications using continuous flow. We always try to dig a little deeper into the mechanistic understanding than to guide us to the design of more efficient catalysts and intriguing transformations. And over the last 3 years, we have also taken the data-driven automation approach, trying to accelerate the optimization and the discovery of new transformations. So throughout this talk, I will try to share 2 most recent research stories. And the first one begins with the methane challenge. So methane, this CH4 molecule, is the simplest organic molecule and represents the most fundamental unit of organic matter. It's commonly recognized in energy-rich resources with vast natural reserves. It's primarily utilized through combustion to produce heat or power, and serving as a cornerstone of the modern energy landscape. In addition to that, enormous reserve of methane also exists in the form of gas hydrates. It exists in the very deep ocean, and high pressure and low temperature, methane and water tend to form a cluster molecule. It's called this combustible ice. So we can easily say that beyond its role as a fuel, methane serves a valuable carbon feedstock, offering unique opportunities to sustainable chemical transformation and carbon resource utilization. But it's truly a challenging task for synthetic chemists. So if you look at this simplified molecule, it only has 4 CH bonds. The molecule is highly symmetrical. And the matrix that qualifies the activity of the CH bond is called the bond dissociation energy. And for methane, is at the top of the chart, 105 kcals per mole. Remember that number. And based on the ionized potential and the proton affinity, it tells us pretty much nothing you can do trying to do a redox or a deprotonation process to try to activate this inert molecule. So this low intrinsic reactivity has made this molecule as a grand challenge in this field, and it has been recognized as the holy grail of catalysis. But this low reactivity has also brought up a different challenge in selectivity. And allow me to demonstrate using these simple transformations at the bottom of this slide. So methanol is a valuable chemical, is a liquid. And if you look at the chemical structure, you will realize methane and oxygen have all the ingredients that you can use to make a methanol: carbon, hydrogen, and oxygen atoms, right? But if you look at deeper, you will realize there's a serious problem, because the CH bond of methanol is 10 kcals molar per weaker than the CH bond of methane. So if you ever find a catalyst that can abstract or activate the CH bond of methane, once the first molecule of methanol can be generated, the catalyst will immediately take the hydrogen atom from this activate product. So it will keep going and going. So even if you have not performed any chemical transformation, I'm pretty sure you have done this experiment already if you ever cooked in the kitchen. So we all know that the main product coming from this reaction is carbon dioxide and sometimes carbon monoxide. So synthetic chemistry have endeavored trying to find a viable solution to make a methanol directly from methane. And what's shown here is a classic Shilov process, where you can use in sulfonic acid, a strong acid, and also an oxidant, and to make, generate methanol in a selective fashion. Of course, you can produce SO2. So since it's a strong acid here, it can protonate the OH of the methanol, or it can react with the hydroxy group here to form a sulfonate, therefore to deactivate the CH bond in the product and making methanol selectively. And with the advancement of transition metal catalysis over the last few decades, there's significant advancement in the direct CH activation of methane using a variety of metal catalysts. And what's shown here represents the latest achievements. 2 research groups in the States managed to achieve the CH boronation reaction with high selectivity. They have to use in rhodium, ruthenium, or iridium catalyst. They have to use in high temperature for them to overcome the activation barrier and sometimes have to suffer from low efficiency. So this is where we started thinking. Taking a lesson from nature does not mean just copy it simply. We have no resources to make this complicated cell factory, but we can take an important lesson to conduct redox chemistry at an excited state to break down the activation barrier. So we started thinking, why not leverage alkoxy radical to do a hydrogen atom transfer from this synergistic sequence and transfer methane into high-valued product. So as shown here in this proposed catalytic circle, the most important step is this hydrogen atom transfer. Even if you don't know this radical chemistry, but it turns into a simple mathematical game. Because look at the number here, the CH bond of methane is 105 kcal per mole. And the OH bond actually is way stronger, it's above 106 kcal per mole. So it can easily, for oxygen-centered radicals, to abstract a hydrogen atom from methane to generate methyl radicals. And kinetically speaking, there is an important principle called the polarity matching effect. So methyl radical is a nucleophilic radical, and alkoxy radical is rather electrophilic. So this process should be kinetically favorable. Once we can produce a methyl radical, we can make it to react with a variety of radical trapping reagents. Most of them have double bonds. For here, if it adds into this azo dicarboxylate, we can easily form a new CN bond to trap that high reactive methyl radical, then generate a relatively stable and also oxidizing nitrogen-centered radical. So this nitrogen-centered radical can oxidize serine-3 to close the serine catalytic cycle. Itself gets reduced, and after protonation, you can generate the desired amylation product. So based on this blueprint, we soon found out that there is a simple solution. We can easily use in serine source in combination with free alcohol as the co-catalyst to achieve this challenging reaction at ambient temperature with blue LED irradiation to provide the energy and redox neutral and pH neutral conditions. We can use in serine trichloride, serine triflate, or serine 4-triflate, which typically recognize as Lewis acid in synthetic chemistry. The turnover numbers can reach nearly to 3,000. And free alcohols, some of them even used as solvent in synthetic labs, such as methanol, terbutanol, or trichloroethanol, can now act as co-catalysts. And importantly, we did not observe any over-oxidation of our desired product or any side product from methyl radical dimerization. So this is indeed a highly selective process. And we can easily swap this azo dicarboxylate to electron-deficient alkane or electron-deficient arene to form CC bonds in this cross-coupling paradigm. So over the last 3 years, we have also conducted a detailed mechanistic investigation. So allow me to talk short here, but I'll quickly walk you through this. So we managed to isolate and characterize the photoactive species, the serine 4 alkoxide pentyl chloride complex. Regarding the critical question, which type of radical can be produced during LMCT excitation, we have been using operando EPR experiments and a transient absorption experiment led us to determine only alkoxide radical was indeed generated in solution, and there's no chance for it to form chlorine radical. And this transient absorption allows us to probe the kinetics in the excited processes, allow us to identify a back electron transfer between the O-center radical and the reduced metal center that causes us quantum efficiency. We have also taken the classical approach of physical org experiments, such as kinetic isotope experiments, led us to determine that this O-center mediated HAT is indeed the rate-determining step. And in collaboration with Professor Hong Xin at Zhejiang University, we have also looked at the KIE experiment and the radioselectivity experiment from the DFT calculations, allow us to know a little bit more about the transition state. And after that, we try to play around with the radioselectivity. And butyne is also recognized as a fuel. But if you look at this molecule more closely, there are two different CH bonds, primary and secondary. Now, either in bond dissociation energy, the bond strength, or the steric environment, those two are very difficult to distinguish. Therefore, recognized as the grand challenge in selective control in transition metal catalysis. So we managed to test a variety of free alcohols, the co-catalysts, and found out that methanol, the corresponding methoxy radical, tends to be the most selective one. It tends to abstract from the relatively weakened secondary CH bond and the more electron-rich positions, leading to the generation of a branched amylation product. And the same selective pattern can be verified on the hexane example. We have also managed to demonstrate scale-up applications in our synthetic lab. This we have to use in a glass-made microreactor made by the Corning company. It's a very small size. You probably only have the half size of your iPhone screen, but it costs way much more, maybe like 5 to 7 iPhones. So we managed to build up a 4.5 milliliter reaction volume using 10 parallel reactors. With that, we can easily achieve up to 2 micromolar per hour productivity. The catalytic conditions we optimize for massing amylation can be easily adopted to other selective functionalization of feedstock chemicals, such as shown here on the right side. We can achieve the serine catalyzed CH amylation of adamantane and to generate this amylated building block for this important anti-diabetic agent. We can achieve satisfactory level of yields and radioselectivity. So now we know how to generate radicals. The next important question is, can we also control its reactivity? One striking example is the CH carbonylation of methane under aerobic conditions. So this is truly a simple and elegant transformation, converting like 2 greenhouse gases into a liquid and valuable chemical, and is vastly produced for the plastic industry. However, this is probably one of the most challenging reactions in selectivity control. So methyl radical is known to add into CO to generate a more stable acetyl radical. But this reaction is known to fail in the presence of oxygen or in the presence of air, because people have studied the kinetics of those two reactions. Obviously, the trapping of methyl radical with oxygen is 3 magnitudes faster than the CC bond formation here. So previously, synthetic chemists have made the judgment call that the presence of oxygen results in a strong inhibiting effect on the formation of acetic acid in the radical chemistry. So you probably have to use chemical oxidants such as persulfate to enforce this reaction. Transition metal catalysis, on the other hand, already made a significant advancement, but also suffering from this side reaction. So the similar report coming from a group at Penn State back in 1994, where they can use rhodium chloride as the catalyst. Basically, rhodium can insert into the CH bond of methane, forming a rhodium methyl species, which can coordinate with CO to form a CO insertion, then generate this CC bond. However, this rhodium methyl species is prone to oxidation. It can be oxidized to generate side products such as methanol, formic acid, or CO2. Almost like 20 years later, a European group tried to leverage this rhodium catalyst on heterogeneous system, and they can significantly increase the catalytic efficiency, but it's the same activation strategy, so they still suffer from the CH oxidation. So the record for this carbonylation reaction is only 2.8 to 1. So we started wondering whether we could leverage the LMCT catalytic platform to enforce the interplay of 1 electron and 2 electron steps to facilitate the CC bond formation. Because we have known to generate methyl radicals from LMCT and HAT event. And in this case, we are wondering whether we could leverage like iron catalysts, because iron 2 are known to coordinate with CO so fast and to generate this iron 2 CO complex. And this complex has been demonstrated previously can interact with alkyl radicals. So if we were lucky enough, if methyl radical can add into this iron coordinated CO, we have a very good chance to form the desired CC bond. And then looking at this, we realize this is sort of like a radical rebound mechanism. And people have studied the methane monooxygenated system. They elucidated that iron oxy cluster could abstract a CH bond from methane to generate a methyl radical. The methyl radical will kick back to this iron complex to enforce the CN bond formation selectively. The only difference here is that before methyl radical interact with our iron catalytic cycle, the CO will jump in to enhance the opportunity to form CC bond. So we started to investigate a variety of iron catalysts and found that iron porphyrin, an icon, I would say, for iron chemistry, could also work in this reaction. It can lead to the generation of acetic acid, although at a moderate level of selectivity, we still suffer from the CH oxidation. So further ligand campaign led us to recognize this terpyridine compound, this iron terpyridine catalyst, which is rather robust for this chemistry, can significantly increase the catalytic efficiency and also selectivity. And the current record can reach up to 20 to 1. We can use in very low catalyst amount of iron catalyst reaching a turnover number of more than 10,000. So this is a classic case where we've shown that we can use in this inexpensive iron catalyst to beat the record set by a low metal catalyst. So we have done some mechanistic investigation, allow us to isolate and characterize photoactive species and done steady state photolysis experiment. We can also monitor the in situ formulation of iron 2CO using operando IR spectroscopy experiment. And through a coordination with my good friend Neil Peng at Pittsburgh, we look at this open shell radical pathway through DFT calculations. Based on their study, that methyl radical can indeed add into this iron 2 coordinated CO through an out-sphere radical addition pathway to generate a more stabilized iron acetal complex. Although currently it's very difficult for us to probe the identity of those metal complexes directly in situ, but I think this finding helps us to explain the peculiar correlation we observed in the optimization. Because back then we realized that the increasing of CO pressure together with the increasing of iron catalyst loading always help us to boost the catalytic efficiency. As you can see from this paradigm here, you will realize that both ingredients increasing the concentration will help you to build up the concentration of the iron 2CO complex. That's critical for the rapid and selective trapping of methyl radicals and keep it from the reacting with oxygen. So I'll quickly walk through the last part, and this is sort of like a side reactions we observed in the CH functionalizing reaction. So when we're trying to manipulate the sterics of our secondary alcohol to play around with the sterics, we always suffer from the beta station, the decomposition of our exact co-catalyst here. So this turns out to be the Achilles heel of our system. So we started thinking out of the box, why not taking this decomposition pathway into a productive activation mode. And by leveraging the alkoxide radical generator from LMCT, we managed to develop a variety of CC bond cleavage and transformation reactions. Basically, we can try to insert a different function group or units into unstrained CC bond, something that previously unheard of pretty much under these mild reaction conditions. And I'll quickly go through the last story. Professor Zhou has shown a lot of exciting chemistry in asymmetric catalysis. I've done a very elegant way, try to elaborate on that point. So we try to start to think outside of the box. So instead of generating the chirality during the construction of the chemical bond, is there any chance that we can impose enantiomer selectivity in reversible reactions? Basically, we can take the exact same molecule, although it's in racemic form, and selectively cleave one of the enantiomer and transfer into the opposite enantiomer without any change in the molecular structure, just the editing of the stereochemistry. This is a new type of transformation called deracemization. We have to overcome the limitation set by the thermodynamics and also the principle of microscopic reversibility. So I don't have enough time to go through all the detail, and also it's a little bit boring for the general public, so I'll quickly walk through this. So we found an interesting strategy, sort of like a one stone, two birds situation. By throwing a chiral ligand in our LMCT catalyst, we can selectively coordinate and activate one of the enantiomer, making to do a selective CC bond cleavage reaction. And at the same time, the generation of a low-valent chiral metal here can mediate alkyl radical addition. If we can do this 1-2 addition asymmetrically, we can achieve our goal and then overcome the limitation of the principle of microscopic reversibility. And so we managed to find out that titanium tetrachloride in combination with chiral phosphonic acid could easily make this reaction work. And this has been demonstrated in a general sense. We can easily manipulate the stereochemistry in a variety of cyclic alcohols, either a strained system or unstrained system. There are cases where we can also editing these court stereocenters. So basically now with this catalytic system, we can easily manipulate the stereocenter of the starting material to get to the opposite mirror image, and then do it again, it will turn into the corresponding same structure once again. So I will quickly walk you through this skip this mechanistic investigation. And through detailed studies, through kinetic analysis, we now know that we can easily achieve good enantiomer selectivity through this multi-pernicative enhancement effect of sterol enrichment. Basically, you don't need to achieve good levels of enantiomer selectivity in each step. 60% EE in the bond cleavage step and 60% EE in bond formation step, basically like a B- results. If they can work synergistically together, you could easily achieve 90% EE in the final outcome. So I have to acknowledge all the heroes behind these stories. And I think my time is almost up. I was thanking this funding situation and thank you for your kind attention.